Okay, so in the following video, we want to talk about the concept of translation in the context of summations. So suppose we have the following summation. We're summing as n ranges, say, from 4 to 7, an, where an is some particular sequence. So if we expand out this summation, well, n starts at 4, so we get a4, then n increases by 1 every time, so a5 plus a6, all the way up to the upper bound of summation when n equals 7. So we have a summation of 4 terms. Now what if you want, say, to translate the index of summation here by, say, 2 to the right? So what if you want to translate the sequence, again, by 2 to the right, so looking at an plus 2, and you ask the following question: how must we change the bounds of summation so that this new version is still the same initial sum? And you say, well, where must n begin so that n plus 2 equals 4? Well, clearly 2 plus 2 is 4, so n must begin at 2. And then you ask, well, where must n end so that n plus 2 equals 7? Well, clearly 5 plus 2 is 7, so n must end at 5. We can verify that this is the same summation as the original by expanding it. So when n is 2, 2 plus 2, 4, so we have a 4. Then n increases by 1, n is 3, 3 plus 2, 5. n equals 4, 4 plus 2, 6. And finally, n equals 5, 5 plus 2, 7. So two different ways of expressing the same summation using sigma notation. And the second one is a translated version of the first. And notice something interesting about how the bounds of summation changed. We increased the index of the sequence by 2 to the right. So we introduced a shift to the right by 2 on the sequence. And of course, if you think about this, well, naturally, if you translate something by 2 to the right, and you want to cancel off this change, this translation, you have to translate back by 2 now on the left. So since we increase the index of the sequence by 2, to cancel this increase, we should decrease the bounds of summation by 2 to offset this translation. So translate 2 to the right, to the left, you're back to where you started, you should get the same summation. And if you notice, that's what happened to your bounds of summation, right? We increased the index of the sequence by 2 to the right by adding 2. To cancel this, we subtracted to the bounds of summation 2. So 7 minus 2, 5. 4 minus 2, 2. What if we perform a different translation? What if we take the initial sequence and translate it now, say, by 3 on the left? So an minus 3. Well, as we've just discussed, if you shift the sequence by 3 on the left, to cancel this translation, you have to shift the bounds of summation by 3. So we are now adding 3 to each lower and upper bound of summation. So 4 plus 3, 7. 7 plus 3, 10. And let's see that we are indeed doing the right thing by expanding out the summation. So of course, when n is 7, 7 minus 3, 4. a4. Then n is 8. 8 minus 3, 5. Then n is 9. 9 minus 3, 6. And finally, when n is 10, 10 minus 3, 7. So it does work. So we can now write this idea into a general statement. So if you have a summation beginning at, say, uppercase M and ending at uppercase N of a given sequence an, if you choose to translate the index of summation by k, so an plus k, to cancel off this translation, you have to then translate the bounds of summation down by k. So begin summing when lowercase n is m minus k, and end summing when lowercase n is uppercase n minus k. And of course, if you choose to translate the sequence not by k to the right, again here assuming k is positive, but by k to the left, and you have a n minus k, then of course you do the opposite. If you translate the index of the sequence by k steps on the left, you have to translate the bounds of summation by k steps to the right, so by adding k. So the sum starts at m plus k and ends at uppercase n plus k. And you might ask, well, why do we care about this? Why, in some cases, would we want to either translate the index of our sequence to the right by some constant or to the left by some constant? Here's an example. What if you have the following summation? Say you're summing n going from, say, 3. Let's go to infinity. Looking at an infinite series, say of the following type, n x to the n minus 2. You might not be a big fan of having x to the n minus 2. You might much rather have x to the n and no annoying n minus 2 to have a cleaner form of the series. So when we talk about power series in this form, so summing powers of x, it's nicer to have x to the n with nothing along with the exponent. Well, to cancel this, we have to add 2 to n. So here we translate the index of our sequence by 2 to the right. So we add 2 to n. So we get n plus 2 here, times x to the n plus 2 minus 2 is of course n. And now we have translated the index of our sequence by 2 to the right by adding 2. To cancel this translation, we have to translate the bounds of our summation down to the left by 2. So we subtract 2. So 3 minus 2, 1. And here infinity minus 2, of course, is still infinity. And this is a more elegant form of the initial series. Of course, both are equal, and you can easily verify this. And I leave this up to you by expanding out the initial series and the new series, and of course you will get the exact same expansion. The reason this is nicer is we have a clean x to the n and not an x to the n minus 2. So you can sometimes take advantage of the idea of translating a summation to get a cleaner version of, in this case, a power series, but of any summation in general.